What? On Q for Q implemented with a circular, doubly linked list with a head pointer. Okay. So I gotta draw pictures with these things, for these things, right? So the way I might draw pictures, and I'm not going to do this in detail for all of this, but for this one I might draw a picture that looks something like this, right? Where I'm just kind of putting blobs on my thing, and I'm pointing to one of the nodes. Now, does it matter which node I'm pointing to, if I'm pointing to where I end or where the data is taken from the structure or where it is added to the structure in the context of this problem? Does it matter where I put that pointer in that? No, that's right. Because, so what gains me that economy? What makes me not have to worry about whether I'm pointing to the front of the queue or the back of the queue? It's doubly linked list. That's right. Okay. All right. So this is a doubly linked list. I happen to be pointing to one element. I can decide whether the front of the queue is, the thing I'm pointing to, or let's see, or the back of the queue is the one I'm pointing to. I get to decide that. I can decide whether, which way it's flipped. Let's do a smell test on this. This is about queues. This is about queues. What do you expect as the on-queue time for queues? Yeah, constant time. So if anything for a queue is not constant time, it means there's something strange about the implementation. Now, this one, can you do it in constant time? Sure. Do you want to decide that this is the back of the queue? Then all we do is we make a new node, make the next node point to this one, and make the back now point to my new node. And this one has to point to the previous here. Oh, and that one has to be updated too. All kinds of pointers have to be updated. But the point is that you can insert the new node where you need to, right? Does it feel okay, or would you want more detail? I can do more detail if you want. It's okay? All right. Let's see. Worst case for finding the maximum value in an ordinary binary tree. Again, I'm going to give myself a sketch. How am I going to find the maximum value? What's the algorithm for finding the maximum value in an ordinary binary tree? Not necessarily BST. Visit every node. And so, how do you visit every node? What algorithm do you run to find every node, to visit every node? Traversal. What's the running time of traversal always? Big O of n. So you're very suspicious if a traversal is not big O of n. So this one is C. This one is A, this one is C. But now things get fancy. Now my little sketch corresponds to a binary search tree. I don't know how to feel about it that people are leaving. Sorry. All right, so now it's binary search tree. So surely we know things about its structure. Surely we're going to do better, right? Are we going to do better because it's a binary search tree? Yeah. It's just a binary search tree. Now we're going to talk about this for a minute, okay? But on first read of this question, you go, oh, I don't know anything in particular about this binary search tree. And but I do know where the maximum value is. It's always going to be over here, right, on the tree. But in the worst case, the whole tree looks like this. And I have to go there to find the max, right? Now, what about if the tree looks like this? What's the running time to find the max? It's big O, or it's n over 2, which is asymptotically the same as n. Okay? So if we don't assume anything about our binary search tree, then the worst case for finding the maximum is this. Now, I'm going to show you something. We didn't read our paragraph up here very and you should assume the best possible implementation given the constraints. What's the best way we know of to implement a binary search tree? Yeah, we should implement that puppy as an AVL tree, right? So I believe we gave credit for log n on this one. Did we? Somebody who said log n, did we? Did we give at least partial credit for it? We gave nothing?
0.5.
0.5 out of 2. If you pushed on it enough, if you came to me with a piece of paper that said, look, it's the best possible implementation, I would have to change the rubric, okay? Yeah?
We wrote C, but like we got mark reductions and the answer is E.
Yeah, we'll get there. Oh, what?
Yeah.
You wrote down E instead?
No, I wrote down C, but I got 0.5 marks off and correct answer is E. Which one? For like the worst case for a binary search tree.
Are you saying the right answer is E or you wrote E?
They are saying the right answer is E.
What? The rubric says the right answer is E?
Yeah. No, it says C. For me, it's C.
No, there is no for you.
Okay, just let me check. Probably like the.
Okay, so I'm happy to revisit the rubric on that. Okay, because that's our error. Yeah?
If you make the binary search tree more balanced, it becomes to log n eventually, but I'm wondering at what point does that asymptote change?
So we only really talked about the extremes of no rebalancing, and so in that context, you are subject to the order of insertion that your data happens to come into, right? So that might already be log n height, if you were lucky. Okay? So, and then the AVL implementation says that you maintain it from the start. So I don't know actually what it means to look at the area in between, because I don't know what an algorithm is to take an ugly tree and to use rotations to turn it into a good tree in time that's faster than it would have taken just to start over anyway. So it's all in the implementation of the whole structure rather than how you change one into another that I think is germane. Does that make sense? Okay. All right.
Oh, guys, like they circled the wrong question.
You circled the wrong one.
No, like they did that mark from circle 4, but this.
Oh yeah, I know. Those boxes, the PDFs are like slightly off, but yeah. So you have to look at the actual question together with what you said. The mapping, the pictures are off on gradestone. They just are. Okay. So now here's another thing that happened was a result of us not reading our own paragraph. We use that paragraph every second midterm we use it, and this time it didn't work quite right. So what does the top say about the value of n? What does it indicate? N is the amount of data, right? What does this problem say about n? The problem implies how many keys? 3n keys, right? So there's this strange, wait, I thought n was what? What is n here? Now, I assert that in this case, it's pretty clear that we intend for you to go ahead and insert 3n keys, right? And that thing up there that we happen to leave in that said n is with the amount of data, we're kind of overwriting that in the context of this problem. Was anybody confused by that in the context of the exam itself? Did that cross your mind? Okay. Yeah?
I'm just curious, isn't that the same? It's still...
Yes, it shouldn't matter. It shouldn't matter. The answers will be the same, which is the key point. But, I wanted to, if that made you feel weird during the exam, I don't know, this is, number one, go with your instinct. Number two, write down what you assume. Number three, we're not out to trick you. We weren't trying to go, oh, take every third one or something. It wasn't that. Okay, so what's the answer here? Initially empty binary search tree. So let's trace through this for just a second. And what we're noticing is these are in decreasing order. And I don't really care about their magnitude. What I care more than anything is their order and the shape that they induce. So I'm starting with the biggest one, and it is the root. How do I insert the next one? Where's it going to go for sure? So I started with 2n. Now I'm doing 2n minus 1. Where's it going to go for sure? On the left. Where, and now here's my tree. Where does 2n minus 2 go? Where's the next one go? To the left again. But I have to find that using the algorithm. So now the running time there is 2 hops, right? And the running time for the next one is 3 hops. To insert the next one is 4 all the way down to we finally insert negative n into the structure. Now let's analyze what we just did here. In the first case, we took no hops, right? There was very little time incurred. Maybe it's a constant amount of time if you want. Okay, well, we'll do it that way. There's a constant amount of time. In the second one, when we inserted the second thing, it took the time it took to compare here, and then insert here. So this is 2. Then for the third one, it took time proportional to the height of the structure, which at that point is 3 minus 1. And then to insert the next one takes approximately time 4. And what you observe is that you're adding up a bunch of values all the way up to essentially 3n, right? Is that clear? Now, if you went so far as to write down this sum, you may be tempted to go down the black hole of going, oh, I know a closed form for that sum. You could do that if you wanted to, but you don't have to. Anytime you ever sum a sequence of numbers of length n, then effectively that's like an additional factor of n. So if you've got n things here, this is, or 3n things here, this is very much like 3n squared. And yeah, you can divide by 2 if you want to. But the upshot is that this is n squared, proportional to n squared. Okay? Any question about that? Seem right? Seem okay? All right. So now, this is E. What's the difference for ABL tree? We're still inserting 3n things. How long do they take? How long does each one take? They take log n at the worst case, right? Now, yes, you're still going to have the plus 1, plus 2. But there's a whole bunch of plus 2s, right? And then once you get all the 2s filled in, there's a whole bunch of plus 3s. And so in the end, like if your n is this huge number, then what you observe is that when you do the insert of, the proportionally to nth one, and you have to navigate the whole height of the structure, that height is log n. Asymptotically, and I know this is all very loose, asymptotically that means that you've essentially incurred log n work for order n operations. You've done order n inserts, each of which is log n in height. Okay, so this must be D. Yeah. Any question about that? Yeah.
I have a question for what? Sir, can you explain why you divided that by 2?
Because half the time I'm a lot shorter than half. I mean, it's very proportional. proportional, right? Half the time I'm kind of shorter than half the length of the list. And for the ones later in the sequence, I'm double that. I shouldn't have. Okay? It was throwing it in there. It was getting you a little closer to this. K equal 1 to n of k is n times n plus 1 over 2. It was kind of talking about that. It was kind of admitting that half the, for those first few, you don't have to go all the way to the bottom. Okay. All right. Yeah?
I just have one question about like the fact that we're using n here.
Yeah?
Like 2n to greater n, but like Bob says, like n is the number of elements.
Yeah, I know.
So that's a little, is that,
It's confusing. Did that confuse you during the exam? Or did you not think about it?
well, I just assumed that like it must be 3n, I guess. Like,
Yeah, right. So the particular question, if it says something that's in conflict with the other one, the particular question wins, right? Because it's more interesting this way also. So making a good bet that what we're talking, and you're welcome to ask us about that in the exam. Okay, you're welcome to go, did you mean this? And we'd have gone, oh, but nobody did. So we didn't even notice it. Okay. All right. Anything else about that? Yeah?
Sorry, for this one, you said for the ADL one, it's log n work per n insert.
Yeah.
That's why it's saying log n.
Yep.
So by that logic, how come it's not, like I get that it's already n squared for the last one,
Yep.
but how come it wouldn't be all one work per n insert?
Because the amount of work each time depends on how many you've seen so far. So if I insert the kth one, so we're talking about the binary search tree where it's all in a line, right? Okay, so if I'm inserting the kth one, the running time of that one depends linearly on the fact that I've inserted k minus 1 before. Now the same thing is going on in the ADL tree, it's true. But logarithms kind of, lots of values of n have the same logarithmic value, essentially, right? Like, what's log base 2 of 8? 3. What's log base 2 of 9? Still kind of 3, right? What's log base 2 of 10? Well, it's 3, and a little bit more, but only a very little bit more. So logs behave differently in this context, that when you're inserting the kth one in the ADL tree, it doesn't cost you significantly more than the previous one cost.
Just because it's bound.
Yes, because the height is log n.
Okay.
Okay? Whereas in the other case, we cannot guarantee that the height is log n. In the worst case, it's not log n. Okay? Does it seem alright? So I know that these are hand wavy. That's why this question is like it is. That's why there's not a half a page for each one of these things, right? Like it's, what's going on in your mind about how these algorithms are executed? Okay? Yeah?
Just a side note, if you have an algorithm and its best case is ON or something, and the worst case is ON, does that mean the average case is theta n?
Is squeezed in. The average case is theta n. It means the case is theta n. If the worst case is less than or equal to a constant times n, and the best case is at least a constant times n, so bounded below, so you can't do any better, so be careful with what you mean by best case there, then the running time overall is not, it is theta of n, meaning it will achieve n and it can do no better. An algorithm cannot do better, okay?
Found it alone.
But be careful about talking about best case, though, because the way I think of best case, as it's usually spoken of in the literature, is as lucky case, right? And that's something very different. That's if your data happens to be arranged in the order that you like. So, is that...
Yeah, that makes sense.
Okay. Yeah?
Just to connect to what we've learned earlier, I think we can, for this case, we could truncate it by half, and then we
Yep.
say log n over 2,
Yep.
and then sum that up,
Yep.
and that's your order,
Yep.
then log n.
Yep. Yep. Yes. Right. Yes.
Just that way we can make it exact.
Yes. More exact. Why n over 2 though?
I'm saying that,
Oh, in the sum of all the logs.
right.
Yeah. I get it. Yeah. So let me try, okay? So what he's observing is that the sum of this really looks like k equal 1 to n of log of k, right?
Is there a K in front of the log? Sorry.
No, because you've got n of them, each of them incur log of however many you've seen. Okay, and so yes, you can do the trick here of going, okay, well I'm just going to add up half of them and consider that to be an upper bound for the total sum, and it will work. You're right. I'm going to hand wave that for right now. Okay, anything else about this? I wish I knew, like, how you guys did on that problem. I don't know, but you don't have to tell me. It's okay. I can go look. All right, rotation in an ABL tree. I'm going to do a rotate in an ABL tree. How much time does it cost? Constant time, that's right. It's like 5 assignment statements, right? The rotation itself is just a sequence of assignment statements. So this is constant time. Okay, the space complexity of a merge sort. All right, we need to talk about this one. All righty. So there are a couple of different things we're going to do here. So merge sort is called on data of size n, and it requires n for the merge. Okay? Now, it is absolutely true that that's the biggest merge among all the recursive calls. That is the biggest merge that you ever have to do, that last merge, right? All the other ones are smaller. So that observation, together with the fact that the merge doesn't happen until both of the recursive calls return, mean that the space is bounded by n. Okay? None of them are going to take more. Now, let's carry that out for a second. So the recursive calls do this, right? There are 2 recursive calls. Now, the one on the left is going to use half as much of the memory, right? It's going to use this much memory, say. But it will not be using that memory at the same time as this one. So it can use the same space. It can use the same memory, the same stacked space, as whatever that one up there used. Any question about that? Is that all right? Okay, and then similarly, and the reason I'm talking about it like this is because we're going to talk about an algorithm which does it differently in just a second. So this one comes all the way down here, and this one uses a little bit less memory, and this one uses maybe just 1 block of memory finally. Okay, and these are all going down by factor of half each time. In the execution, this one gives back its memory. This one is still not using its. This one comes and it does its and it gives back. So by the time we use this block, that's the only thing I need. It's the only memory that's live. Any question about that at all? Okay? And so the space complexity of merge sort is, what's the answer then? What's the implication? N. That's right, because you use n at the top. It's the most you ever use. Each one of those is a decreasing smaller factor of n. Now, but you do use n because that merge requires the whole thing. You can't say n over 2. You can't say log of n. You have to say you use the whole n. Okay? All right, now I want to present kind of a different algorithm. You can imagine an algorithm that laid out numbers in an array, then made a recursive call, which also laid out numbers in an array, and then made a recursive call, which then laid out numbers in an array, in which case all of these would be live, essentially being used at once. Oh, there's one more thing to talk about merge sort too. So that all of these would be used at once. How much memory is that? It feels like ON squared, right? Feels like it. Feels like maybe n log n. This is a cool thing. This is a really cool thing, okay? So I'm going to lay out the original n. Okay? So I'm just going to give myself a yardstick, which is n. Okay? And I'm going to use that n. But now I'm thinking about, okay, how much additional do I use here? So let's start adding them up. What's the first recursive call use? How much memory does the first recursive call use? Half n. So it uses this much, right? How much does the second recursive call use at the same time? A fourth of n. So it uses this. How much does the third recursive call use? Whatever a half of a fourth was, wherever we are in this, right? How much does the next one use? Well, a half of what's left. How much does the next one use? A half of what's left, down to the base case, which only uses one or none, right? So how much memory do I use if I use that whole span and then give back this one and use it again? So how much do I ever use? N? No, I used n at the top. 2n, that's right. So that's kind of cool, right? That in the end, you're thinking, well, they're log n levels and it's a factor of n every time. The thing is, it's better than a factor of n every time. It's a decreasing factor of n every time. It's a geometrically decreasing piece of n every time. Yeah?
What if we just never freed any memory?
I'm going to ask you that next. So what if our algorithm never gave anything back? So that's adding up all those rectangles, right? And how much is in each row? How much is in each row? There's n in this one, there's n over 2 plus n over 2. Oh, there's n in this one. These are all n over 4, but there's 4 of them, so there are n in this one. So if nobody ever gave memory back, every level would be order n, and how many levels are there? Log n, that's right. So the most this could use, if nobody ever gave any memory back, the largest footprint that it could have in memory is n log n, which is really good news. That's not that much bigger than linear. N log n is awesome. Okay? Any question about that? I really wish that I had had the lucidity to talk about that in class, and I don't know where that went. Okay, so this one is, the final answer here is? Oh, no! It is. I'm teasing. Yes, it's C. Sorry, that was too... I've been in this room a very long time. All right. Here's another one that I wish we had asked differently. But we spent a fair amount of time in class on it, so we'll see what you think here. All right, so quick short. Okay. All right, so how does quicksort work? Here's my array of values. Those values are already in order, and I do not care whether they're increasing or decreasing. I don't care, okay? Now, here's how our algorithm in class worked. Great. Who's in Jeff's class here? Okay. Do you want to tell me how yours worked? And I'll tell you if ours was the same. How did quicksort work? Which one was the pivot? Which element did you choose as the pivot?
Last set.
Last one, yes, us too. Phew, right? Okay, so we're going to choose the last thing as the pivot, and then we're effectively going to figure out where it goes. Now, what does the partition look like? If we choose the last thing, what's the partition going to look like? Just like that, right? And we're only going to know after that one iteration that we have put that one thing in place. Now, when we recursively go to the left, we're going to choose the last one and then partition. And what does the partition look like? That. Now, let's write a recurrence that captures this. This is bad, bad, bad behavior. The running time of, this is bad quicksort, on data of size n is the running time it takes to finish with the rest of the data plus, what's the additive term? What's the additive term here? Yeah?
I'm not sure exactly. N minus 1 or n.
Yeah, it's n or n minus 1, I don't know either. Okay? But I'm going to write n here. So what does that mean? If I unroll this recurrence, what sum do I get? N plus n minus 1 plus n minus 2. If I unroll this all the way down to the bottom, I'm going to have the sum of the values from 1 to n. And we well know at this point that that has magnitude n squared. Okay, so in the worst case for quicksort, or quicksort on an array already in order, we get n squared, and none of these is appropriate. Are you happy with that? Yeah?
No, because it said that we can assume it's a best case implementation, and he said in class that if we felt that our list was likely to be sorted, then you just picked your pivot randomly. And if you picked your pivot randomly, then you back to n.
Yeah, right. That's right. Yeah. You put n?
Oh,
The rubric says that the answer is n plus n.
Yeah, but you don't know why.
It's because of the order.
Yeah, so this question drives me nuts. Because what we intended to get from you was E, right? That's the straightforward algorithm that we gave uses that last thing as pivot, and it does very poorly on sorted data. So we thought you're going to get E there. But that's only the quicksort algorithm that we know about. If you can give yourself a good pivot, which is what you're talking about, right? If you can give yourself a good pivot, then you're going to get n log n. Can you give yourself a good pivot in the worst case? In the worst case, can you give yourself a good pivot?
Square one array.
So, I mean, in the worst case, meaning for any, any data, can you always give yourself a good pivot? So the answer is, okay, so the answer that we know about is you can do things to make it likely that you get a good pivot, right? You can, randomly draw 3 of them and take the middle of those. That improves the likelihood that you get a good pivot. You can, I don't know, there are probably measures of displacement that you can do on your data in linear time. You can get a good pivot that way, though, since you're partitioning linear time, I'm not sure that helps you. But here's the thing. So if you're lucky, yes, you can get a good pivot. Or if you induce randomness into selecting your pivot, you can get a good pivot. There exists an algorithm that guarantees a good pivot. And that's what you don't necessarily know about in this class because you study it in 320. And so when people answered this one, D, I have no way of knowing whether you said D because, you know, you're working hard and you found the deterministic select algorithm approach to quicksort. And so you know that there is an algorithm that in the worst case will get quicksort to n log n. You might know that. I also don't know if you just got lucky, right? Like you say, I don't know, feels like n log n. I don't know, I'll never know. So we gave credit for both of them, okay? You should have received credit for both, equal credit for both of those answers. Yeah?
So, in a way, it's arcane order.
Yeah, but you don't necessarily know that. Okay, okay.
I'm just saying that it's really bad to run quicksort on a rate that's already in order.
Yeah, but what if you don't know it's already in order?
So you could just, I guess, verify.
Yeah, so you, I mean,
You could just like,
yeah, yes, you could go through and you could get some measure of displacement, right? In fact, yeah, and then decide what to do with your data. In fact, guys, you remember homework 2? What was the criteria for that you could use that stack sort? What was the criteria? If it didn't have a bum in it, like an up, down, like that, then there's a linear sort. Is effectively what it was. So you could pre-scan your data for that and decide if there's no that characteristic, then you can use a stack and sort linear time, right? So sorting can be this more like nuanced thing, but that's not where we are. And sorting is not interesting, right? Like says the person with a jumbled up sock drawer. Okay, what else? What else? Okay, so we did this. Yes? On the what? I'm sorry, what?
On the rotation question.
Yep.
What if it has rebalancing? What would the time be?
The what?
If it has rebalancing in an ABL tree, what would the
Alright, so if you remember, in the worst case, in the very worst case, which is upon removal, you're going to incur rotation, which is constant time, at every level of the tree. So that's constant time per element of the height, which just means your running time is still proportional to the height. It's just that your constant is bigger. Right? Does that make sense?
Yeah.
So even if you had to rotate all the way up, you're still only incurring a constant factor. You're still asymptotically still proportional to the height of the tree.
Even if you don't need to rotate all the way up? Like,
Even if you don't need to rotate up.
still need to search.
Yep. Yep. In the worst case, you're hitting the bottom of that structure. Okay? All right. Any other questions about any of these? Okay. Apologize for the little blips in there. Oh. Okay. We should talk about this one, right?
Yes.
Yeah. Okay, let's do it. Sorry. Okay. So when you think about zero child remove, it's just a snip, right? And when you're snipping things off, it doesn't really matter where you do them. It's just a snip, right? And when you're snipping things off, it doesn't really matter where you do them. You're not changing the structure of the tree. When you do one child remove, when you remove something with one child, you don't rearrange things in the tree. Everything that used to be a child of something, the subtrees all stay the same. They move around a little bit, but they stay the same. When you do two child remove, you take something from the bottom and you put it to the top, which means it has different children than it had before. Now, a couple things go on. One is that it can change the structure of the tree. And the other one is, as we see in the next problem, I wish to, with all my heart, that I had said, let's just do one of these and not the other. It can break what you assumed about an ordering in the case of a tie. So these two pieces of this problem are really closely related to one another. Okay, so you're going to affect the height of, or the structure of this tree. We've already sort of gotten in the headspace of we probably need a two-child remove. And so I really don't know any other way of approaching this problem except to kind of look at two-child removes and see if how much they change the structure of the tree. Okay. So, when I was solving this as rough draft, I really literally was doing these things in my head quickly, right? Like I was doing it in a kind of exhaustive way. There was no principled, 31 has blah, and so it must be part of it. There was none of that. It was, I'm going to try pairs, guaranteeing that one of which is a two-child remove, and see what I come up with. And maybe I would gain insight as I did this. Okay, so where do you want to start thinking about this? Let's think about what it means to remove 53. It's sitting there staring at us. If we remove 53, that's really like removing 42, right? Structurally, that's like removing 42. So those are kind of the same. Yeah? Is this supposed to be a different shape or a totally different tree? Oh, shape, different structure. Yes, compared to moving B first then A. Okay, and if I remove 42 then, what happens? If I remove 53 and then 42, then that was sort of like, structurally, that's exactly the same as if I snipped this one off first and then did a two-child remove here. So 53 and 42, which was by far the most common incorrect answer, removing 53 and then 42 is the same structurally as removing the leaf first and then the root, right? Does that seem okay? Because removing the root means you bring that 41 up. So it's really like you removed the 42 to begin with. Okay? Seem all right? Okay, so neither one of those is good. I'm going to think about removing 31. So if I remove 31, I mess up that dangle. Right? I got the 18 dangling down there. If I remove 31, now 18 comes up here. And now I can remove lots of different things, and I will forever have changed the structure of this subtree. Right? So what else could I remove? Well, I don't know if it works if you remove 18. No, it doesn't. Because then 9 comes up, and that's what would have been anyway. So, let's see. So what I'm going to do is remove something that would force this 918 thing to remain if I had done it first. Does that make sense? So, I've already moved the 31, 18 is up there, 18 is gone. And if I remove 42, my structure looks like, like 9, 18, 53 across the top. Okay, my structure, if I remove 31, then 42 looks like this. Okay, any question about that? If I remove 42, 42 and then 31. If I remove 42, then 31 becomes a one-child remove, and that 18 is never swapped up, right? And so, I remove 42, 31 is now a one-child remove. Structure of the tree afterward looks like this. 9 goes to 18, these have all been moved up, and so now instead of, and now I've got this angle over here. Okay, any question about that? It was a matter of facility with removal and being able to very quickly see the effect of making a pairwise decision and sort of going through them principally. Yeah?
When you remove 42, is there a rotation?
These are not ABL trees. These are not ABL trees. Oh!
Yeah.
No!
I spent hours on this question thinking it was an ABL.
Me too.
No! No, the rotation question comes later.
Like right after, no, they were like next to each other. So no matter how much you tried, it would look the same. So it was like the biggest time suck in the world.
I'm using the same ABL, but like I don't know why.
Yeah, it was definitely our fault.
This ABL,
Yeah, yeah.
And this one we were explicit about it not being an ABL tree, so there's nothing in your mind going, oh, I wonder if the other one, like there's nothing here that would make you,
Yeah.
okay. Okay. I kind of liked this test when it was first, like, I'm like, oh, lots of little puzzles. Yeah. All right. So, I remember this moment in class where somebody said, what do you do when we're talking about binary search trees? We are using them sort of as implementations of dictionaries. And that means we get to assume unique keys. Yay! We get to assume unique keys. And I'm pretty sure that, even I will say, don't worry about it. If you have a tie, just put it on the right or left, as the case may be. Right. Yeah, right. Just put it on the right. We'll find it later. Here's the thing. That's broken. And this problem is asking you to show that it's broken. Now, it's broken if you do removals, is the story. So if you, depending on how you batch your removals or what your removal algorithm is, it's broken for our removal algorithms. That's the right way to say it. Okay, so that's what this question is all about. So all you have to do is figure out a way to insert another 67, which is going to put it in this one's right subtree, and then do some removals. So it's going to put it here. So put in another 67. There has to be true, 2 of them. Then do some removals that effectively put the 67 up here so that now all of a sudden there's a 67 in the left subtree instead of in the right where it belongs. Now the implication for this is that if you're searching for 67, yeah, we didn't remove one, right? if you're searching for a 67, a different 67, you know, like maybe I'm looking for the second 67, right? I'm looking for the second 67. My insertion algorithm said, if you see a 67, look on the right. That clearly won't work if, when I remove, I do this two-child remove thing. Right? So that's the point of this whole problem. Any question about it? So the sequence is, if some of this doesn't matter, you have to insert another 67, and then you need to remove the 71 to kind of get it out of the way, because right now it's the in-order predecessor, and then remove 78. Okay? Yeah? The reverse order, sure. Yep, absolutely. And some people removed it all. Some people removed everything and then just rebuilt it. Like, okay, you go. Fine. Yeah? Oh, you guys are collinear. Go ahead. Okay, go ahead.
I don't get why we need to when it says the node has to be in the left subtree of the one closer to the root.
Yep. It's called the higher one. The higher 67 given of the two 67s, it has to be in the right subtree of the one that's closer to the root. What?
Do you mean left subtree?
Yeah, no. Sorry. Yeah.
And then, like it doesn't matter if it was the original 67.
No, there.
Then I don't get why, like, what's the point? Because
Okay.
it's just not removing 78.
Well, it's the 78 that pulls out above. Okay. We tried to get those, but I don't promise that we got them. Yes. Did you get the clarification, the clarified wording during your exam? Yeah. So we gave clarified wording. Oh.
So, what I'm confusing with the question was where it says that you get the hearing in the left subtree of the node closer to the root.
Yeah, so right where we are talking about the two 67s, the pair.
Had the question being asked to do a series of removals and insertions such that 67 appears as the left child of 67. But the way that the question was worded made no sense.
So, more than anything, I wish I could give the exams to you guys to proofread for us for clarity, but I can't. So, here's my modification. That thing, that happens to everybody at some point, right? Everybody who's engaged and working hard on this, something will happen that is like unfair about the process. And so what that means is that we sort of have to go like, oh yeah, it sucks when it happens. It's not destroying the curve. Like it's happening uniformly. It's kind of an artifact of the fact that we live like we use language. We try really hard to be clear. And honestly, I think our instructional material, don't get me wrong, I think, of course, our instructional materials are usually pretty clear. We try really hard. So,
Yeah, I don't mean this as like a criticism. I am curious though of all of the students who wrote the exam and how they got full marks for that particular class.
I can look afterward. I can go into, well, I don't know my grade scope password on this machine, but I can go look and see what fraction of students got this one right. It's not high.
I suggested if they were very low fraction.
That we reduce the number of points.
Unfair.
Yeah, I mean, believe me, we've done some rubric adjusting to, I hope, accommodate for some of that. But I'll take a look at it again. Absolutely, I'm happy to do that. Yeah?
I remember that PA was like clarifying what was done on the board before, so it's just
Yeah, that's the thing, is that so some classes will say, you may not ask questions. We don't do that, right? Like, I want to know how people are processing the language. So I know it's putting some burden on you, but go ahead. And even for this question, probably 5 people asked before we finally said, no, that must just not be clear. And that was when we made the attempt, I'll say it that way, the attempt at a clarification. So, yeah, I'll look at the rubric again though, and make sure that it kind of, I don't know, that it does the right thing, given what you're saying. Okay. That's the thing I want to make sure doesn't happen. I want to make sure that if you did get it, then the mark won't go down. Yeah. And moreover, I can't switch out the weight. I can't decrease the weight of the question, right? Because that means I'm going to take something that you did well and put it on something you did sucky on. So I'm not doing that either. So I'm pretty careful with how we do this. Can I skip the merge sort question and go to the reverse the list question? I'm almost done here. I'm just almost done. So let's go to what I think is the harder question. All right. I draw a picture of a list here. Do you care? Let's see. How are we now? That's all the code. Here's my list. Okay, so here's the one when I was describing what we were going to do tonight. This is the moment where I think I want to give you some things to think about. The thing that's embarrassing is what I'm really going to say to you is trust the natural recursion. I'm sorry. I have now bought into the meme. At the university that I came from, we would have said that as trust the recursion theory. So a little more fanciful, but the same sentiment, all the same. And in my undergraduate experience, it would have been rely on your inductive hypothesis. It would have been much less fanciful and fun, much less joyful, which isn't entirely true, but it's all the same. So that's the large piece of it, and we'll walk through this and I'll show you how that applies in just a second. The other piece of it is when you have a linear structure, the recursive substructure goes like this. The recursive substructure is the first element of the list and the rest of the list. So if you're doing something that's linear on a linear structure, it would surprise you a lot if the recursive call were not on the next thing. Okay? Any question about that? And that's where I start. Okay? So that's where I start. I don't start with the base case. I'll deal with that later. Those are easy. So I'm going to start with that recursive case. Okay? to be very surprised. So now we've got this pointer called ND. ND, which is the parameter that comes in. This is the state of memory. And what I'm going to do is call reverse recursive on, what does it mean, given what I just said? Reverse recursive on ND next, like that, right? Okay, any question about that? So now, given that, I want to draw a picture of what I expect out of that, okay? So what do I think has happened as a result of this? That is, what is reverse recursive going to hand back to me that I'm now going to call NB? Well, I don't know for sure, but what NB is going to do is hand me back a pointer to this one, which, it's going to point to this one, it's going to point to this one, and this one is going to be null. Right? Yes? Right? Do you agree? I could draw that picture the other way if you want me to. Here, I know the easy way to do this. I'm going to put data in here so you can see what's happening. So my data is A, B, C, D. My original list looks like A, B, C, D. What I get back, if I draw a picture of what NB points to, the first thing it has is D, the next one it has is C, the next one it has is B, and that's it. Dang. Shoot. Too bad. Okay? Any question about that at all? So this little sketch up there is the same as this green drawing here. And I'm going to assume that's what I got. Yeah?
How did you assume that the thing that was given back was going to be the head pointer?
I need to have a handle on it, right? I gave away a handle on the array. All right, here's ND next. ND next. Okay, so I started with a handle on the rest of the list. And what I'm going to get back is a handle on a reversed list. That's it. Okay, clear? So I didn't really think of it as the head. I just knew that's how I was holding on to it. Furthermore, it's a singly linked list. If I don't have that one, I'm never going to be able to see that one. So that node. Okay. So are we in good shape here? No, we're not. Where does A need to go? Where does A need to go in the little sketch? Where does A need to go? So I've got the reversal of the list. Where does A need to go? Oh, the end. Oh, crap. So A needs to go here. A would be easy to connect if only I had a pointer to that last thing, right? If only I knew where that was, then I could reattach things, right? So I need to plan ahead. I need my recursive magic to do just a little bit more than what I asked it to do before. I need it to also have a pointer to the last thing. How can I do that? Oh, crap. You see how to do it? Yeah, look. I've got a variable here. I've got a variable here. It's there for me to use. Moreover, before I do any switching around, I know ahead of time what's going to be at the end of the recursively reversed list, right? So I'm just going to stick in this little pointer and let it go. So I'm going to set NA to be, what's the assignment? How do I get NA set up to be the thing that I want. That is what appears up in this picture. What is it? ND. ND. I want it to point to B, right? I want it to be pointing to B. So I'm just going to make it point to ND next. Yeah? And then, you know, NA is always going to hold the memory address of that thing that holds B, right? And it will still be there after the recursive call comes up. I'll still have that memory address. So now it's easy. Yeah, I'm not even going to be embarrassed to say it's easy. Now watch me make a mistake, right? So now my setup is this. I've got NA, I have ND pointing to the front thing. I don't really care what this is at this point. I'll make it null explicitly in a sec. And so now all I have to do is reset this pointer to do this. Can I do that? NA next equal what? NV, right? It needs to point to the same box that NV points to, has always pointed to. Okay? Now, I've picked up ND, so I've put NA where it needs to go. The last thing is this one, let's see, where did it used to point? It used to do this. Oh, I could have done that. So it needs to be null, that's right. So ND's next needs to be null. And what are we going to return? NB. There you go. Done. That's it. Okay. So what? Yeah?
Can we do this before the final?
Do this thing before the final, like with a practice final? Yeah, sure. Is it really?
No, it's helpful.
Okay. Yeah, sure.
What about the statement?
Oh, those base cases. Oh, yeah. Okay, so in what cases do we not have to do any work? If it's empty, or if it has one element, right? The reversal of the one element list is that. So I'm going to write it down with a bug, and you're going to tell me what the bug is, okay? So it's if ND next is null, or if ND is null, I'm going to return ND. Okay, because either way, if it's null, I'll return null, no big deal. If it has one thing, I'll return that and say, oh, look, sorted reverse list, done. So what's the bug here? There's like a half point error here, I think. Yeah?
You can't call that next, but that is
Right. This is broken. You should have an early warning system anytime you dereference anything ever, right? If ND is equal to null, your code's going to segfault when you check next. So it turns out in Java and in C++ that the OR operator is not commutative, which drives me completely nuts. I would not have written this code this way. I just said if this, and then if the other case, else if the other case. So what you have to do is you have to check ND first. And then it will drop out. If ND is equal to null, it will drop out. Otherwise, it will evaluate this one. Okay, there you go. Yes?
So when you think about recursion,
Mm-hmm.
are you always thinking about it in terms of like, I have part A and part B, and then just assume that the rest works? How do you
inductive proof, do you want to like apply the inductive hypothesis at every level? Do you want to do that? That's what you're doing. It's exactly the same. You want to go talk to Gregor? I remember the minute the trust was like real, when the romance really got serious, right? Like, I remember that feeling, oh, I could do anything. Like, once you really believe it, the design element becomes different, right? Like I don't know, you don't have to unroll things, and you don't have to think about how your recursive case interacts with your base case. That's the part that drives me completely nuts, right? It's like, okay, well, does it work in this base? Don't even think about it. Think about the base cases. Think about the recursive cases. Done. Yeah, it's crazy. I love it. Even after sitting in this room for... Okay. What's up? All right, where are we? Yes, we can do this for the final. I want to make sure it's like sort of fair. So we probably actually will do it in a room where it can be recorded. And we'll announce it earlier. And it may be after class, like we're done with class. What I think is going to happen is that the last week of class is going to be all about graphs, and we won't actually have done anything about them with them, right? Because we're past any of the homework, we're canceling the last programming assignment, and then all of a sudden we'll be at the exam. So I think it's really a good idea to do some practicing on problems about graphs especially. So yes, I'm game. It's fun, right? Yeah? Yeah, so here's what I'm going to do. Here's how I do the programming assignments. I have 4 of them. They have particular learning objectives attached to them, but I change them every semester. So what I'm going to do is give you last semester's anyway. I'll put it on the website even. I'm not going to do the adaptation that I would have done specifically for you guys because I want to use that next semester. Sorry, but I think the learning objectives that you get out of it will be the same. You'll be able to see. it. And I mean, I guess you could crowdsource a solution. Maybe I don't know if I want to give the solution. It would feel really weird to like say, here's a whole assignment and the solution. That would feel weird to me somehow. Yes, absolutely. Yep. Yeah. Okay. What's up?
Full set of test cases.
For that 4th one, we weren't using Gradescope. I'm not sure those exist. We'll see. Let's see what I can pull. I'll try. We'll see. I don't know how much focus you're going to want to have on the 4th one. The 4th one is very much like the 2nd one, honestly. It's really kind of cool because it's very much like the 2nd one, but it solves a completely different problem. Yeah?
I was wondering if number 5 is curved at all, since like that section covers recurrence relation for the midterm, and your section covers it like over the week before. So was it curved at all between the different sections to account for that? Is number 5?
No. So Jeff and I cover things differently, in different orders and at different depths. Like, he goes way faster than me, and I tuck little things in all along. So while he covered them only for that day, that's all he did on that day. I covered them, it's true, I covered them over a week, but I didn't cover merge sort separately from that. I tucked the recurrence into the conversation about merge sort, and that's really all I did, right? Like it isn't like there was a lot of, I don't know, did you guys not feel very secure about it anyway, right? Like, I gave recurrences for ABL trees even. Did you guys have recurrences for ABL trees? But it was just tucked in. Like they were just little, little pieces. I don't think think the magnitude of the way we addressed any particular thing is vastly different. Okay, that's my feel. I think his way of doing things works better for some people, and mine works